Hello everyone, Mr. John here with this week's Thursday Tidbit. Today we are going to be revisiting geometric probability, looking at an example and seeing how it relates to some more advanced topics such as conditional probability as well. Let's jump right in then. As a quick review, when we are doing probability, the main formula we always want to stress is the probability of an event A is the number of ways to get what you want, or some measure of the number of what you want, and some measure of the total. So typically, as I was mentioning, this can be the number of ways that you want. If you roll a die, one side is a 2, there are 6 sides in total, the probability is 1/6. But if you're doing something geometrically, you're picking a point on a line or something that can be represented like that, like a time between 9 and 10 a.m. That is an infinite amount of times, that's an interval of time. You can pick that then as a length. You can measure want as a length, total as a length, or area. Want and total can both be areas, and that pattern can work for a lot of different geometric quantities or other quantities there as well. Seeing that in an example, let's suppose we are choosing two numbers. So here we have a real number x from the interval 0 to 4. Our first variable here is x, and this is going to be picked on this number line from 0 to 4. And so if we're dealing with just x, we can deal with lengths, different things like that there. The probability that x is bigger than 2 is 1/2, because that would divide this interval into 2 equal pieces, etc., etc. We would have different patterns for that there. Y is now chosen between 0 and 2. So we could also think of y as being an interval from 0 to 2 in this scenario. Now, we want to then talk about x and y. What is the probability that the lengths x, y, and the number 3 can be used to form a triangle? Now, the main thing I want to introduce on this page before we solve this on the next slide is that rather than thinking about x and y separate, x in a number line, y in a number line, well, let's do what we do in the coordinate system. We learned about number lines first, and then you can put two number lines together, x and y axis, and then you can be picking a point in two-dimensional space. So the real first key I want to talk about here is that we can think about then x and y as being chosen in a box rather than a number line, or rather than separate number lines. We have almost a coordinate system here where x is in the x-axis. That's why you can start seeing where the variable names came from here. And then we have the same thing for y in the vertical axis here. So we could have 0, 1, and 2 in this scenario. And then any point that we pick, notice now we can pick a point in two-dimensional space. For example, if I pick this point here, that of course corresponds to roughly at least x is equal to 3 and y is equal to 1. Now we can think about this as one single process there. You pick a point, and that point gives you the x and y values, and then we can start figuring out when does this form a triangle and things like that from that point forward. Okay, so let's look at the summary of the question and look at our grid here that we have made for us so we can have a little better picture of what's going on. Still again, we have x is the horizontal x-axis in our grid, and y is our vertical y-axis in our grid. And then we want to think about when can these lengths be used to form a triangle in this case. Now, probably you can see, but if we're just listening to the video, what is our key geometric fact we're going to use for when can these lengths form a triangle? Of course, that is going to be the triangle inequality. So we need these three lengths to satisfy the triangle inequality. And we do want to be careful with that because we don't necessarily know how the lengths will work with each other. We don't know the longest length, we don't know the shortest length, etc. So we need to do all three versions of the triangle inequality, at least to be safe. We'll say, I'll make some comments on this in just a second, but I want to just think about this as three statements. X plus y has to be greater than 3. We need then that x plus 3 has to be greater than y. And of course, we need then y plus 3 to be greater than x. We need all three possibilities in the orderings of these inequalities. Two sides in a triangle always need to add up to at least longer than the third side. Now, are all of these relevant in this case? Well, no. The second one is actually just true. Remember, y is being chosen between 0 and 2, so x plus 3 is definitely bigger than 2, which is bigger than any possible y we're going to get in that scenario. So that one we don't have to worry about here. Let's think about the other ones, however, one by one. What has to happen for x plus y to be bigger than 3? I oftentimes like thinking about these as lines first. So we have x plus y equals 3, and that is of course a line with slope of -1 going through the point 3 there. So you draw the full line first. Y needs to be bigger than this. You could also just plug in points to see which region you want. And we therefore see we have to be above this line in that case. So let me shrink it to our rectangle, and we will see that every portion in this trapezoid here will satisfy x plus y is bigger than 3 in this scenario. Now, we can play the same game on the other inequality. We need y plus 3. Let me highlight it quick. Y plus 3 to be bigger than x in that case. So this is saying that y is again bigger than x minus 3. So this is a line with slope of 1 going through the point 0, 3. Again, I can shrink it to the portion that we need in our triangle, or in our rectangle there. And we need all the y values above that. So that again is a shape that we have here, highlighted in orange as well. Now, what we really want is all of these things to be satisfied. We said the second one is always true, but let me delete them separately and combined. The two that we want in all is going to be this little quadrilateral region here. This region is going to be what we want. Any point in this region will give us x and y so that x, y, and 3 can be used to form a triangle. So, if we calculate our probability from here, remember probability we can still think of as want divided by total, except here our want and total are in terms of area, of course. We want to be thinking of area in this case. So our total area is, of course, 2 times 4 is 8. There's lots of ways to calculate this area here. It's pretty easy otherwise to count the squares and triangles or break it down. So one way to break it down would be like this. You can actually break it down into unit squares and triangles with area 1/2. So regardless of how you do this, we have an area here just counting up of 3.5 in the region we want. So if we wanted to simplify this as a final answer, we would have 7 over 16. There's a little less than a half chance that we can form a triangle with these 3 lengths. 2 of them randomly chosen, and then the length of 3 at the end. Okay, let's do a quick review now of conditional probability, and then we're going to revisit this picture from before. So, conditional probability of A given B. So you can think of this as you're given extra information in a problem. The probability of A given B, again, you can think of this as the ratio want divided by total, except now your total is the given B portion. We have the probability of A and B happening divided by the probability of B. And remember, we can write this with the intersection. The upside down U is the set notation for and, this intersection region between the 2 sets there. But when you're given that information, it becomes the new total, and everything happens in that region. That's why our numerator is A and B, A intersect B, because we want to make sure that both events are happening in that case. So how does this apply to our scenario we were just looking at here? So just to remind us of what we just did, this region here we had was our region of the place we could make a triangle with these side lengths there. So this region was the probability that we can form a triangle in this scenario. So if we choose these numbers as before, maybe let me label the x and y quick. Given that we can make a triangle, what is the probability that x is greater than or equal to 2? Now, just revisiting very basic, if you just ask the question straight up without anything given, what is the probability that x is greater than or equal to 2? That is, of course, a half. There's 2 out of 4 in this interval is x greater than or equal to 2. So that would be a half without any information given. But now we're being told, well, what if you can create a triangle? So we know we can create a triangle. What is the probability that x is greater than or equal to 2? Intuitively looking at our picture here, most of this region is x bigger than 2. So we would suspect this to be quite a bit larger than 1/2. And that's actually going to be very true, and it's pretty intuitive how we calculate this anyway. Now let me just do it the formal way we described on the previous slide. So let's let A be the event here that x is greater than or equal to 2. We have B is the event that we can form a triangle. So let me just write that out in shorthand here. We can form a triangle in that case. And our formula, just straight up following the formula, says the probability of A given B, which is exactly what we're looking for here. Given that we can form the triangle, what is the probability that x is greater than or equal to 2? And this is therefore equal to the probability of A and B. So A intersect B divided by the probability of B in this scenario. So we already know the probability of B. Just to remind ourselves of that, that was our 3.5 over 8, which is 7 over 16. Let me actually just write this as 3.5 over 8 as a preview of something we are going to do I'll mention at the bottom in this case. But let me write this as 3.5 over 8 in this scenario. So now we need to look at this intersection of A and B. What does A intersect B look like? And what does that probability look like there too? Well, if we want x to be greater than or equal to 2, that is this box here. But whenever we're doing the intersection then, we need both of those regions to come together. So if we're looking at the intersections of those two regions, we in fact have this little pentagon, this house-shaped region right here. This is going to be the intersection of A and B in that case. So that is our intersection, and we can therefore calculate the probability of that intersection the exact same way we did before. Notice there's nothing given, so that little house region pretty easily has an area of 3. The whole shape still has an area of 8, so this becomes 3 divided by 8 in this scenario. So we end up with 3 over 3.5, and so our final answer here is going to be 6/7 in this scenario. That is our final answer for this probability in this scenario. Now, let me go back, and you probably see some suspicious numbers here. If we focus on this 3 over 3.5, this isn't totally following the formula, but this logic works there as well. A lot of the times, people just like doing the geometric version of conditional probability or whatever directly with a want divided by total, and you can still think about it as areas. So we want A intersect B. Well, that is this house-shaped pentagon in red we just talked about. That has an area of 3. And where can you intuitively think of the 3.5 directly? You can think of that as the area we have in blue. So that red region plus the little blue region, which was the area we could form the triangle. So because they're in the same sample space, because we have the same 8 as the total area, a lot of the times if we were actually doing this directly, if this was the one problem we needed to solve, the way I would recommend thinking about it would be, okay, we want A intersect B divided by our total of B. Rather than doing those both as probabilities, express them as a ratio of areas. So the area where x is bigger than 2 and we can form a triangle, divided by the area where we can form a triangle, and that would get us to our same answer in that case. That will do it for this video then. Please check back each Thursday for another math tidbit for the rest of 2021. And we have a lot of great other resources on ziml.areteem.org. Join the community over there, the Zoom International Math League. A lot of great things, daily problems, monthly contests. We also have other archives for AMC problems, things like that as well. Hope to see everybody next week for the new tidbit and also in the community on ZIML. Goodbye.